Welcome to the Deep Dive. We're here to unpack recent machine learning research, pulling out the key insights so you can stay ahead.
Yeah, keeping up is tough, so we try to make it a bit easier.
Exactly. And today, we're diving into a really interesting paper tackling a challenge that's, well, it's becoming quite critical. How do you remove specific data from a trained ML model?
Especially when those removal requests aren't, evenly spread.
Right. Which happens a lot in the real world.
The paper's called Group Robust Machine Unlearning. It's got authors from several institutions, University of Trento, Telecom Paris, Inferior Grenoble, and Fondazione Bruno Kessler.
And it's super relevant because of privacy rules like GDPR, right? That whole right to be forgotten thing.
Precisely. That's a big driver. People want their data out, but how do you do that efficiently and fairly?
Okay, so machine unlearning. The obvious way is just retrain the whole model without the data you want gone.
Yeah, the gold standard, you could say. But imagine doing that for, like, a giant language model.
Billions of parameters.
Yeah.
Retraining every time someone asks. No way. Computationally, it's just not going to happen.
Exactly. It's completely infeasible for large models. And that's where approximate unlearning comes into play.
Trying to get the model to forget without the full retraining cost.
Right. But here's the catch that this paper really focuses on. Most existing methods sort of assume the data being forgotten is, well, random, uniformly distributed across the data set.
But life isn't usually that neat.
Not at all. Unlearning requests often come disproportionately from certain groups, maybe based on profession or location or some other attribute. They call these non-uniform forget sets.
And the problem is, if you just use standard unlearning methods on these non-uniform sets,
you can actually hurt the model's performance specifically for the group that's overrepresented in the forget requests, even for the members of that group whose data wasn't removed.
Ooh, okay. That sounds like a fairness issue.
It absolutely is. Think about a recommendation system. Maybe lots of, say, young men request their data removed. A standard unlearning method might then make the recommendations worse for all young men still using the system.
Right, because the model lost too much information specific to that group. That's the overlooked problem they mention.
That's exactly it. How do we unlearn non-uniformly distributed data while being robust for those dominant groups in the forget set? That's the core mission here.
Group Robust Machine Unlearning. Okay, got it. So the paper aims to give us a way to do that, remove data, but minimize the hit to these specific groups.
Precisely. They start by really defining the problem clearly. They point out the limits of current methods with these uneven forget sets.
Do they show examples?
They do. Figure 1 gives a nice visual showing how accuracy for a dominant group can drop with standard unlearning versus their proposed robust approach.
And they use that recommendation system example.
Yeah, but you can easily see it applying elsewhere. Facial recognition, maybe. If you unlearn data mostly from one demographic.
The model might get worse at recognizing faces from that demographic overall.
Yeah, I can see that. And they actually show this happening. Figure 2 in the paper details experiments on the celeb data set. They tried unlearning data for attractive males, using standard methods like L1 sparse, saloon, scrub. As they removed more data from that specific group, the model's accuracy for attractive males dropped quite a bit.
So clear evidence that the standard approaches have this vulnerability.
Definitely. It really motivates the need for a new strategy.
All right, so problem established. What's their solution? Or solutions?
They offer 2 main contributions. First, for what's called exact unlearning, which, remember, is basically retraining on the remaining data.
The expensive way.
The expensive way, yeah. They propose a method called reweight, and it's actually surprisingly straightforward. The intuition is, if you remove a bunch of data from one group, the remaining data, the retained set, is now skewed. It doesn't represent the original distribution anymore.
Right, is missing representation from that group.
So reweight compensates during retraining. It increases the likelihood of sampling data points from the groups that were partly unlearned.
So you're giving more weight to the examples you still have from those underrepresented after unlearning groups.
Exactly. You rebalance the statistics of the retained set to better match the original training data's group distribution.
How do they calculate the weights?
It's based on the ratio. They look at the frequency of each group in the original full dataset versus its frequency in the dataset after removing the forget set. That ratio tells them how much to upweight certain samples.
Okay, that makes sense.
Yeah.
How does this reweight compare to other methods that try to handle group fairness, like group DRO?
That's a great question. They did compare it. Group DRO, Group Distributionally Robust Optimization, tries to improve the model's performance on the worst performing group overall.
Right, common fairness technique.
But when they applied Group DRO in this exact unlearning context, they found some weird things happened. Sometimes the accuracy on the data they were trying to forget actually went up.
Whoa, wait, that's the opposite of unlearning.
Exactly. Counterintuitive. And sometimes the overall test accuracy dropped too. Reweight, on the other hand, seemed much better at just preserving the original model's group robustness and test accuracy after retraining on the reweighted retained set. Figure 3 shows this comparison pretty clearly.
So reweight seems more targeted for this specific unlearning scenario, avoiding those unintended side effects of just boosting the worst group.
It seems that way for exact unlearning, yes, but again, exact unlearning is often too costly.
Right, which brings us to approximate methods.
Exactly, and that's their second and arguably main contribution, an approximate unlearning method called MIU. That stands for Mutual Information-aware Machine Unlearning.
MIU.
Oh.
And they claim this is the first approximate method really designed for group robustness with these unbalanced forget sets.
That's their claim, yeah. It tackles the efficiency problem while keeping group fairness in mind.
Mutual information. Okay, let's unpack that. What's the core idea? How does mutual information help here?
So mutual information basically measures how much information two variables share, like how dependent they are on each other. In MIU, they focus on the mutual information between the features the model learns and the group labels of the data points in the forget set.
The features and the group info for the data being removed. Why?
The idea is, if that mutual information is high, it means the model's internal features are strongly linked to or predictive of the group attributes, like male or attractive in the celeb example. These might be spurious correlations you don't want influencing the unlearning.
So you want to break that link.
Precisely. They aim to minimize this mutual information on the forget set. By doing that, they hope to decouple the unlearning process from these group attributes, making it fairer and preventing that performance drop for the dominant group.
So it's not just about making the model output the wrong answer for the forgotten data, but actually weakening the internal representation's connection to the sensitive group info itself.
That's a good way to think about it, yeah. It makes the forgetting less dependent on those group characteristics.
Interesting. Is that all MIU does? Minimize that MI?
No, it's actually got three main parts working together in its objective function. That mutual information minimization on the forget set is the first, the unlearning term.
Okay, part 1. Decorrelate features in group info for forgotten data.
Part 2 is a calibration term. They realize that just focusing on the forget set might mess things up for other groups in the retain set.
Right, fixing one problem might create another.
So this calibration term tries to keep the unlearned model behaving similarly to the original model in terms of group robustness across the data that's kept. It does this by minimizing the difference in mutual information patterns between the old and new model, but calculated on the reweighted retained dataset.
Using their reweight idea again.
Yep, using reweight to ensure the comparison is fair given the changed distribution. It encourages the unlearned model to sort of mimic the original model's group robustness profile.
Clever. Okay, unlearning term, calibration term.
Yeah.
So the third.
The third is the retaining term. This is more standard. It's basically just optimizing the model's main task performance, like classification accuracy, using cross-entropy loss, but again, calculated on the reweighted retained dataset.
So make sure it still does its main job well while accounting for the data imbalance using reweight.
Exactly. So you have these three components. 1, unlearn via minimizing MI on forget set. 2, calibrate to maintain original robustness on retain set. And 3, retain core task performance on retain set, all using reweight to handle the distribution shift. Equation 6 in the paper shows the combined objective.
Okay, that sounds like a pretty comprehensive approach. How did they test it?
They used 3 standard data sets often used in fairness and vision research: Celeba, Waterbirds, and Fairface. These have clear target labels and also protected attributes, which is key here.
And they compared MIU against?
Against several existing approximate unlearning methods, they mention L1 sparse, Saloon, and Scrub as baselines. We don't need the nitty-gritty on those, but they represent the state-of-the-art that doesn't explicitly consider group robustness in the same way.
Got it. And what metrics did they track? Obviously accuracy, but what else?
A whole suite. Retain accuracy on kept data, forget accuracy, how well it forgets, overall test accuracy. Crucially, also membership inference attack success rate, a proxy for privacy.
Lower is better for privacy there.
Right. And for group robustness, they looked at things like equalized odds, the actual accuracy on the dominant forget group, and an average gap metric comparing performance to the ideal retraining with reweighting scenario.
So the big question, did MIU work? Did it achieve group robust unlearning better than the others?
According to their results, yes. Tables 1 to 3 and figures 4 and 5 show MIU pretty consistently outperforming the baselines. It did a better job of preserving the accuracy and fairness metrics for the dominant forget group while still achieving effective unlearning.
And they saw that link between forgetting well and group accuracy.
Yeah, they noted a consistent correlation. It suggests that when MIU effectively reduced the model's reliance on the specific information from the dominant forget group, its performance on unseen data from that same group became more stable and closer to what you'd expect.
That makes sense. If it truly forgets the specifics, it should generalize better based on the remaining data for that group.
Exactly. They also tested different scenarios, like varying the percentage of data being unlearned from the dominant group.
How did MIU handle that?
It showed more stable performance compared to the baselines across different unlearning ratios. They even looked at multi-group unlearning, where the forget set had high representation from multiple groups, not just one.
And MIU was still robust.
Apparently so, yeah. Their results suggest it handled those more complex scenarios well, too.
Did they do an ablation study? Like turning off parts of MIU to see what matters most?
They did. Table 4 and Figure 8 cover that. It showed that each component, the unlearning term, the calibration term, and the retaining term, played a significant role in the overall effectiveness. They all contribute.
Okay, solid experimental backing then. This feels like a really important piece of work. Maybe we can step back and think about the context. Where does this fit in the history of machine unlearning?
Good idea. So machine unlearning itself, as a field, really took off because of privacy concerns and regulations, especially GDPR around 2018.
The right to be forgotten.
Exactly. Initially, researchers focused heavily on exact unlearning, trying to get mathematical proof that the forgotten data's influence was totally gone.
But we already said that's often too slow, right?
Right. The computational cost for big models just became a major roadblock, which naturally led to the rise of approximate unlearning methods.
Faster, maybe not perfect guarantees, but practical.
That was the trade-off. And in those early days of approximate unlearning, the main focus was just on how to make the model forget, efficiently tweaking gradients, adding noise, stuff like that.
But not necessarily thinking about who was being forgotten.
Pretty much. The potential fairness implications, the fact that unlearning could hurt specific groups if the forget requests weren't uniform, that was largely overlooked. The default assumption was kind of this ideal, evenly distributed forget set.
Which, as this paper points out, is often not realistic.
Exactly. It seems like a typical research progression, right? Solve the core technical challenge first, then realize the broader impacts and start addressing those.
Like fairness.
Precisely. This paper is significant because it explicitly connects machine unlearning to the whole field of fairness in ML, which has blown up in recent years. It's applying that fairness lens, specifically group robustness, to the unlearning process itself.
So, quick summary of the innovation. They spot the problem of non-uniform forget sets hurting dominant groups. They offer reweight for the exact but slow case. And crucially, they propose MIU, using mutual information ideas, as the first approximate method truly designed for group robust unlearning.
That captures it well.
Yeah.
And the real-world importance here is huge. Companies need ways to handle data removal requests, not just legally, but to maintain trust.
Yeah, it's not just compliance. It's about responsible AI. If your unlearning process makes your model biased or unfair,
you've got a serious problem. Think about facial recognition, personalized medicine, credit scoring.
In all those areas, unfairness introduced during unlearning could have really bad consequences for specific groups.
Absolutely. So this research is pushing towards ML systems that can respect privacy without sacrificing fairness. It's about building more reliable and equitable AI.
Okay, really interesting stuff. Let's shift gears slightly to our novel notions segment. Building on this paper, what are some potential future research ideas? Where could this go next?
Well, one interesting direction could be developing ways to automatically detect these dominant groups in forget requests, especially when you don't have explicit labels like male or attractive.
Oh, so unsupervised group detection for unlearning.
Exactly. Imagine you run a big language model and suddenly you get a spike in unlearning requests, all seeming to relate to some specific, maybe controversial topic, but you don't have a label for interested in topic X. Could an unsupervised method look at the embeddings of the data being requested for removal, find a cluster, and say, hey, there's a dominant implicit group here we need to be careful about during unlearning?
Using clustering or representation learning on the forget requests themselves? That would make these techniques way more applicable, wouldn't it? If you don't need predefined protected attributes.
Totally. It would broaden the scope significantly.
What else?
Another idea could be using adversarial learning, but for unlearning robustness. Maybe during the initial training of the model.
How would that work? Train it to be resistant to unlearning damage from the start.
Sort of. You could train a critic network alongside the main model. The critic's job would be to try to find groups whose performance drops significantly after simulated unlearning events.
Like an adversary trying to break the model's group fairness via unlearning.
Yeah. And the feedback from that critic could then be used to make the main model learn representations that are inherently more robust to having data removed later on, especially for specific groups.
Interesting. Like adversarial debiasing, but focused on the unlearning process itself.
Exactly. Drawing inspiration from adversarial robustness training in other areas. It could lead to models that are just fundamentally more privacy-preserving and fair when faced with real-world unlearning demands.
Those are definitely some thought-provoking directions. It shows how this paper really opens doors.
It does. And of course, a quick reminder to everyone listening, these novel nations are just speculative ideas, food for thought.
Absolutely. Okay, let's wrap up this deep dive. We've looked at the critical challenge of non-uniform forget sets in machine unlearning and the fairness problems they cause.
We discussed the reweight strategy for exact unlearning and the MIU approach for approximate unlearning, which uses mutual information to tackle this group robustness issue head-on.
And we've highlighted why this is so important for privacy, fairness, and building trustworthy AI systems.
Definitely check out the original paper if you want the full details, links in the description. It's a really solid piece of work.
And one final thought to leave you with. As privacy rules keep evolving and users demand more control, how will that constant pressure continue to shape the future of machine unlearning research and technology?
Something to ponder.
Thanks for joining us on the Deep Dive. We'll catch you next time for another exploration.